Hello and a warm welcome back to my YouTube channel. Today we're going to be looking at gaseous volume relationships, some concentration calculations, limiting reactants if I get time, and this may well go into some titration type calculations. We'll see how time goes. If I have to break off and do something else, then so be it. So let's begin. 1 mole of any gas, doesn't matter which gas it is, will occupy the same volume. The amount of gas is the volume divided by the molar volume, and for the iGCSE syllabus, 1 mole of gas occupies 24 dm cubed, which is the same as 24,000 cm cubed. So deci means 10, so forgive my cube here, but it's 10 by 10 by 10. 10 cubed equals 1,000. Okay, so 1 decimeter cubed equals 1,000 centimeters cubed. Right, so remember 24 dm cubed, and we'll call that the molar volume. So you must check that you use molar volume in the same units as the volume of the gas. So if it's in dm cubed or cm cubed, it matters. Just remember 1 dm cubed is 1,000 cm cubed. Okay, let's have a look how this works. So here we have a problem. How many moles of gas are there at room temperature and pressure in 48,000 cm cubed of carbon dioxide? At room temperature and pressure, we don't have to worry about that too much at GCSE. Certainly for IB standard level, you would have to worry about that, but I'll save that for a separate video. So it's going to be 48,000 divided by, well, the molar volume in cm cubed is 24,000. So that will be 2 moles of CO2. Cool. 120 cm cubed of sulfur dioxide, so that's going to be cm cubed again. So that's going to be 120. I'll improve my handwriting. 120 divided by, 24,000. And that's going to equal 0.005 moles of, this is sulfur dioxide, SO2. You could also express that as 5 by 10 to the minus 3 moles of SO2. We're not bothered, it's okay. Now we've gone from cm cubed to dm cubed, so we'll use the 24 instead. So it's going to be 4.8 divided by 24, which all you mental arithmeticians will be 0.200 moles of ammonia, which is NH3. Okay, another type of problem. What volume will the following quantities of gas occupy at room temperature and pressure? It says room temperature and pressure just to keep us happy. That's all good. So what's the volume? Well, if 1 mole has a volume of 24 dm cubed, then 5 moles must have 5 times 24, which I make 120 dm cubed of NO2, which is nitrogen dioxide. 3 by 10 to the minus 3 moles of hydrogen sulfide. So that's 3 times 10 to the minus 3 times 24. Let's put this into cm cubed. 24, 1, 2, 3. Why am I choosing cm cubed? Well, it's such a small 0.003 moles of hydrogen sulfide that my answer is going to be more manageable. So that's going to be 72 cm cubed of H2S, which is 0.072 decimeters cubed, but I think you understand. 72 cm cubed is much more pleasing to the eye. Okay, 0.1 moles of argon. So it's just 0.1 moles, so it's 0.1 times, what's the molar volume? 24, so it's going to be 2.4 dm cubed of argon. Again, with the handwriting theme, let's keep that legible. 2.4 dm cubed of argon. Cool, okay. So, next type of problem, convert the following masses of gas into moles. So we're going to convert mass into moles. We're going to have to use moles is mass over molecular mass, aren't we? So the MR of CH4 equals, well, carbon is 12 and hydrogen is 1, so it's 12 plus 4 times 1, so that equals 16. So the 12 came from the carbon, the 1s came from the hydrogen, that equals 16. So the amount, or the moles of methane, moles, remember, N is M over Mr, moles is mass over molecular mass, so the moles is going to be the mass in the question, which is 1 times 10 to the minus 4 divided by the molecular mass here, which is 16, which I make 6.25. Do that again. 6.25 times 10 to the minus 4. Beg your pardon. Not too many decimal places. Times 10 to the minus 3 moles. So now I have moles, the volume will equal the moles times 24, as we have been doing previously. So it's 6.25 times 10 to the minus 3 times 24,000. Same as the one above, it's a small number, so use the cm cubed, which equals 0.15 cm cubed of methane. Okay, the same strategy as before, 0.11 grams of carbon dioxide. The MR, let's do that first, the molecular mass of CO2 is going to be 12 plus, that's a plus 2 times 16, that equals 44. This is grams per mole, this is grams per mole, 44. So the amount of CO2, moles is mass over Mr, so amount of CO2 will equal 0.11 divided by 44, which equals 2.5 times 10 to the minus 3 moles. And next to the volume, times it by our 24,000, so it's 2.5 times 10 to the minus 3 times 24,000, and that equals 60 cm cubed. Okay, 1 gram of hydrogen, so the MR, get the molecular mass first, of H2 is 2 times 1, which equals 2 grams per mole. The amount is 1 divided by 2, so the moles is 1 gram over 2 grams. Moles is mass over Mr. That obviously equals 0.5 moles. 0.5 moles. Now just to get the volume, you've got it. So it's going to be 0.5 times 24 is 12 dm cubed. Let's use the happy purple pen. There's the answer. Okay, so hopefully there are enough examples there for you to grapple with any of the molar volume of a gas type of problems. We're now going to have a look at concentrations, as I mentioned at the beginning, so the concentrations of solution. So the number of particles per unit volume is concentration. It's what chemists use to work out potential masses of products that we could get, or limiting reactants. Let's have a look and see how we do. So the concentration of a solution is measured as the number of moles in a cubic decimeter. We mentioned on the previous page, a decimeter is a cube 10 by 10 by 10, which is 10 cubed, which equals 1,000 cm cubed, which equals 1 dm cubed. You may have come across these. These are volumetric flasks of different volume, and we put accurately known masses into accurately known volumes of water and make it up to the mark using distilled water for purity. Okay. The unit of concentration is moles per decimeter cubed. You can put it moles dm to the minus 3, or just big capital M for molarity, not to be confused with MR, which is the molecular mass. Yes, chemistry puts all the same letters, meaning completely different things. Thank you, chemistry. So a 1 mole solution contains 1 mole of solute dissolved in water to make up 1 decimeter cubed of solution, and we call that 1 mole per decimeter cubed, or you'll probably find bottles just labelled as 1m. The moles in solution triangle, well, C equals N over V. This is concentration. This is my moles. This is my volume. And if you like your triangles, you're going to get CNV. Okay, so now you can put your finger over any of those values and work out the unknown. Okay, so start off nice and simple. Calculate the amount in moles 2 decimeter cubed of 1 mole per decimeter cubed sulfuric acid. Well, if we're working out N is going to equal C times V, isn't it? So N equals C times V from my triangle. C is concentration, which is 1, V is 2. So that's just going to be 1 times 2, which equals 2 moles, number 1. Number 2, now instead of it being in decimeter cubed, it's in cm cubed. So I have to change that to decimeter cubed. How do I do that? Well, I take my 500 cm cubed, I divide it by 1000. Remember, 1000 equals 1 decimeter cubed. And we're going to times it by 2, because it's a 2 mole per decimeter cubed solution. So it's half of 2, which equals 1 mole. Same here, 250 cm cubed. I'm going to have to convert my cm cubed to decimeters cubed. 250 divided by 1000 times the concentration, which is 1, and that's going to equal 0.25 moles. Go again, 100 cm cubed of 0.5 mole per decimeter cubed sodium hydroxide. Convert cm cubed to decimeters cubed, that's 100 over 1000, times 0.5, I make that 0.05 moles. And finally, you're on a roll now. 50 divided by 1000 times 0.01 from the question equals 5.0 by 10 to the minus 4. I hope you're happy with standard form moles of sodium chloride. Okay, so rules for masses in solution. So this is working out what's the concentration from a known mass. Identify what you know. So it will normally give you a mass. It could give you a volume. Let's have a look. So it can either give you mass, and then we know that N is little m over big M. So we can work out moles from the mass and the molecular mass. That's one way they could do it. So if they give you grams, you're using the moles is mass over Mr. equation. We've just been doing some gaseous volumes. Remember, volume, it could be, so we know that 1 mole is 24 dm cubed, or 24,000 cm cubed. That's all good. So either of these relationships, 1 or 2, should be enough to get you through most mole problems. Okay, let's have a look at number 1. Nice and straightforward, I hope, to begin. What mass of sodium hydroxide must be used to make up 250 cm cubed, a 0.2 mole per decimeter cubed solution? So, there we go. Right, the amount of moles needed, moles. So what do we have? We have volume, and so we have V and C. And we know that C is N over V, so N equals C times V. So concentration is 0.2 times the volume, which is 250, you remembered, well done, divided by 1000, that equals 0.05 moles of sodium hydroxide. So now we've used equation 1 to get our moles, which is N. Now we're going to use equation 2 because we know that it's 0.05 moles, so I want to know what's the mass. How do I work out mass? Well, moles is mass over Mr. Let's do that again. So N is little m over big M, so we can solve for mass. So part 2, we need to know the molecular mass of sodium hydroxide. So sodium is 23, oxygen is 16, and hydrogen is 1. So look in your periodic table. Please use ptable.com, that's one of my favourite websites. Sodium 23, oxygen 16, hydrogen 1, that equals 40 grams per mole. But we've got 0.05 moles and a molecular mass of 40 grams per mole. So the mass of NaOH will equal 0.05 times 40, because we want mass, which is mR times moles. So that equals 2 grams. What does that mean? Well, I would need to use 2 grams of sodium hydroxide, so I've answered the question, what's the mass of sodium hydroxide, to make up a 250 cm cubed of a 0.2 mole per decimeter cubed solution. Okay, let's look at this one. What mass is needed to make up 500 cm cubed of a 0.1 mole per decimeter cubed solution of sodium hydroxide? So start as we did last time. So moles HCl, N equals C times V. Moles is concentration times volume. Our volume is 500. You got it? Divide it by 1,000 to put into decimeters cubed. Times it by 0.1 because that's the concentration. I make that 0.05 moles, and that's of the hydrochloric acid. The MR of HCl, well, hydrogen is 1, chlorine is 35.5, so that equals 36.5. So if I take my moles, 0.05, times it by the MR, 36.5, I get the answer of 1.83 G. That's the mass in grams to make up 500 cm cubed of 0.1 mole per decimeter cubed solution of hydrochloric acid. Okay, let's go again. Potassium hydroxide, what's the amount of potassium hydroxide? N equals C times V. Concentration is 0.25. Volume is 200. Easy now, right? Divide it by 1,000. That's going to equal 0.05 moles. The MR of potassium hydroxide is going to equal 39.1 plus 16 plus 1, which equals 56.1 grams per mole. So the mass needed is the moles times the molecular mass. So it's 0.05, that's from here, times the molecular mass from here, which is 56.1, which equals 2.8 G. And then the last one of this type, 300 cm cubed. So what we're going to do, well, we need to know the amount of H2N moles of H2C2O4. We've got 300. You got it. Divide it by 1,000 to make it into dm cubed, times by 0.125, and I make that 0.0375 moles. Now what's the MR of H2C2O4? Well, it's going to be 2 plus 12 times 2. That's a plus, Mr. Minchley. Plus 12 times 2, plus 4 times 16 for my oxygen, which I make 90.0. So the mass needed is going to be 0.0375 times 90, which equals 3.38 G to 3 sig fig. Okay, cool. Moving on then. What is the concentration of the solutions? So the 0.26 G of sodium hydroxide in 100 cm cubed of solution. Well, what's the MR of sodium hydroxide? What's the molecular mass? It's going to be 23 plus 16 plus 1, that equals 40 G, that's the molecular mass. So moles is mass over Mr, and is little m over big M. So we've got 0.26 G, so it's 0.26 divided by 40, which I equal 0.0065 moles. And this is in, so we've got concentration is moles over volume. Volume is 100 cm cubed, so C is N over V. These two equations and 24 dm cubed for 1 mole of a gas will get you flying colours on any GCSE question. So now it's 0.0065, so C equals 0.0065 divided by, well, it's 100 cm cubed, which is 0.1 decimeters cubed, which equals 0.0, just move it one to the left, 65 moles per decimeter cubed. This is definitely sort of A-star GCSE territory, probably more like IB standard level calculations right now, if you're getting a little bit worried. Okay, the MR of copper sulfate. Copper is 63.5, sulfur is 32, plus 4 times 16. I make that 159.6. The amount is moles is mass over Mr, so it's 20.4 given in the question, divided by 159.6, which I make 0.1278 moles. So concentration is moles over volume, so I've got my moles, which are here, so that's going to be 0.1278. What's my volume? It's 275 cm cubed, which is 0.275 dm cubed, which I make that 0.465 moles per decimeter cubed. Then the last one, you know what to do now, right? What's the first thing we're going to do? It's the MR of CaCl2, where calcium is 40.1, plus 2 chlorines, that's a plus 2 times 35.5, that equals 111.1, rolls off the tongue. So the moles is going to equal the 0.05 G in the question, 0.05 divided by 111.1, I make that 0.123345 moles. C equals N over V, so we're using this one. First we use this, then we use this. The moles is 0.00045, divided by 125 cm cubed, which is 0.125 decimeters cubed. That equals 3.6 by 10 to the minus 3. Let's use capital M because I'm running out of space. Okay, you can convert directly between two different concentrations in solution. So if you're going for concentration in moles per decimeter cubed and you want concentration in grams per decimeter cubed, let's have a look at how we do that. So calculate the concentration in moles per decimeter cubed of each of these. So hydrochloric acid containing 36.5 grams per decimeter cubed. Those with a good memory will remember that HCl does indeed have a molecular mass of 36.5, but let's just do that. So MR HCl is going to be 1 plus 35.5, which equals 36.5. So the concentration, well, the concentration is going to be the 36.5 divided by 36.5, which equals 1 mole per decimeter cubed. So this is changing between grams per decimeter cubed and moles per decimeter cubed. That's quite a trivial example. Let's look at something a bit more involved. Not that much though. Looking at the numbers, I know those numbers off by heart. So the molecular mass of sulfuric acid is going to be 2 times 1 for the hydrogen, plus 32 for the sulfur, plus 4 times 16, which I make 98.1. So concentration will equal 9.8 over 98.1. So it's grams per decimeter cubed divided by the molecular mass. If we put that into our calculator, it's going to be 0.1, near enough, but let's be correct. 0.0999 moles per decimeter cubed. Question 5, calculate the concentration in grams per decimeter cubed of these solutions. So first of all, where do we begin? Wherever we can. So the MR of HCl is 36.5. That's the third time we've done it, so if you're not sure why that is, then please just flick back in the video. So the concentration is 0.2 times 36.5, because it's 0.2 moles per decimeter cubed. That equals 7.3 grams per decimeter cubed. Water concentration in grams per decimeter cubed of a sulfuric acid solution containing 0.5 moles per decimeter cubed. Where do we begin? Well, the MR of H2SO4 was 98.1. Where are we? Up here. It's still 98.1. So C is going to equal the 0.5 times 98.1. So it's half a mole, which equals 49.1 grams per decimeter cubed. Okay, so moles and reactions. We're doing okay for time, I think. Yeah. So we can use balanced equations to find the stoichiometry of a reaction and calculate the amounts of chemicals reacting or produced in a reaction. Reacting masses, why are they important? Why do we care? Well, one, they're on the syllabus. That means you should care. Number two is, if you were in industry, your factory manager could come and say, how much do I need to add of reactant A and reactant B to make my product X, and will it be profitable to do that? So that's a real world application. Rules: write a balanced equation, we can do that. Write down the ratio of the moles. If masses are given, then convert to moles, we can do that. It's just moles is mass over mister. Use the ratio, and then convert the moles into the mass. So this is, again, this is probably more like just A star sort of iGCSE, definitely going into standard level IB or even AS level, if that's your syllabus. Okay, so here's an example. What mass of calcium oxide would be formed if 25 grams of calcium carbonate were decomposed? Okay, so our first step was a balanced equation. So we've got that. CaCO3 decomposes to make CaO and CO2. The amount was 25 grams, so it's 20. So this is using moles, is mass over mister. So that's 25 divided by the sum of the atomic masses to get the molecular mass. So it's going to be 25 divided by 100, which equals 0.25 moles. The reacting ratio is 1 to 1, so if there's 0.25 moles of calcium carbonate, which is this one, then there's 0.25 moles of calcium oxide and 0.25 moles of carbon dioxide. That's why we do the balancing of the equation. So moles, N is little m over big M, so M is N times big M, and this is this, so this is my moles, this is my mister. The mass of calcium oxide made is 14G. All good? Cool. Okay. So let's have a look at this one. What mass of copper sulfate is made when 225 G of copper carbonate, right? I always write my numbers from my questions underneath the reactants or the products, and you'll find that continues through the IB videos as well. It helps me, hopefully it helps you. 225 G of copper carbonate. Excess means there's too much of it. There's loads of it. If you were trying to make some cheese sandwiches, my students will probably laughing now because I use this in class. There are way more slices of bread. This is my bread. This is my cheese. If I had 4 slices of cheese, I could only use 8 slices of bread. There'd be lots of bread left over. We're starting to hint at limiting reactants here. Is this balanced? Copper 1, 1, carbon 1, 1. Oxygen 3 there, 4 there, that's 7, that's 2, 3, add 4 is 7. Sulfur is 1, it balances. So what do I need to know first? Well, I've got 225G of my copper carbonate. The MR of copper carbonate is going to be 63.5 plus 12 for my carbon plus 3 times 16 for my oxygen. That equals 123.5 grams per mole. So the moles of CuCO3 is going to be 225. Let's start that again. I'm supposed to be working on my handwriting. 225 divided by 123.5. Okay, 225 from the question, 123.5 from the sum of the atomic masses. That equals 1.822 moles. So what's the moles of copper sulfate? This one, well, the reacting ratio is 1 to 1, so NCuSO4 is equivalent to NCuCO3, so that's also going to equal 1.822. Now I need the MR of copper sulfate, which is 63.5 plus 39.1 plus 4 times 16, that equals 159.6. So if I times my 159.6 times 1.822, that equals 290, let's go 3 sig figs, 291 grams of copper sulfate when 225 G of copper carbonate reacts with excess sulfuric acid. Happy? Okay. These ones is when the reacting ratio is not 1 to 1. We've got time to do a couple more, so let's just see how we go. We may well just get 2 more done. So we now have a 1 to 2 reacting ratio, magnesium with hydrochloric acid. So there's 1 magnesium and there are 2 HCl's. The amount of magnesium used was 6.075 grams. That was in the question. That's 0.25 moles. The amount moles of hydrogen is also 0.25 because it's a 1 to 1 reacting ratio. So the volume of hydrogen made, now we're using our molar volume of a gas, which is 24, is the number of moles of magnesium, which equals the number of moles of hydrogen. So it's 0.25 times 24, which equals 6 decimeters cubed. Okay, calculate the volume of hydrogen evolved at room temperature and pressure when 3.27. What I've been telling you to do, write the numbers you're given in the question underneath the reactant. So it's 3.27 grams of zinc. Excess, that's my bread, loads of bread, lots of bread left over. So the moles of Zn equals 3. That was terrible. Start again. Equals 3.27 divided by 65.4, which is the atomic mass of zinc, which equals 0.05 moles. That means the moles of H2, well, it's 1 to 1, zinc to hydrogen, is going to equal also 0.05 moles. So the volume of hydrogen produced is 0.05 times 24, which equals 1.2 decimeters cubed. Next one, what volume of nitrogen dioxide is evolved at RTP, or room temperature and pressure, when 18.54 G of magnesium nitrate are fully decomposed by heat? Right, well the ratio here, what volume of N, this one, it's 2 to 4. So we're looking at the relationship between the magnesium nitrate and the nitrogen dioxide. 2 to 4, I'm sure you all know, is exactly the same as saying it's 1 to 2. It's just double. So where do we begin? Where we can. The MR of magnesium nitrate equals 24.3 plus 2 times 14 plus 6 times 16. I make that 148.3 grams. The moles, therefore, well, I've got 18.54, so N is 18.54 divided by 148.3, which equals 0.125. So the moles of NO2 is 0.125 times 2 over 1. Why is it 2 over 1? Because that's the reacting ratio. So that equals 0.25 moles of my NO2. Now I'm home and dry. My volume of NO2 will equal 0.25 times 24, which equals 6 dm cubed. Okay, well, we'll leave it there for today. That's as much as I wanted to do and to achieve. Hope you found this useful. Please subscribe at the bottom, like, comment.